This video is meant for Mrs. Rose's AB Calculus class, and it is on the Fundamental Theorem of Calculus, Part 2. We are going to start off with an example. Our capital F of x equals the integral from 1 to x of t plus 2 dt. Our goal is to find the derivative. So, since f of x equals this, the first thing we're going to do is integrate using the first fundamental theorem of calculus. So capital F of x equals 1/2 t squared plus 2t, and we're going to evaluate at 1 and x. So plugging in my x value first, we're going to get 1/2 x squared plus 2x, and then we're subtracting 1/2 plus 2. Okay. Simplifying it just a little bit, we've got 1/2 x squared plus 2x minus 5/2. And our goal of the problem is to find capital F prime of x, and so now we're going to take the derivative. And we get x plus 2. If you notice, x plus 2 is pretty much the same thing as t plus 2, it just has an x. And so we make this the second fundamental theorem of calculus. If f is continuous on an open interval containing x equals a, then for every x in the interval, we have this theorem. The derivative of an integral from a to x of f of t dt is just equal to f of x. So this is some of the directions that you'll see in your textbook. Integrate to find capital F as a function of x, and then demonstrate the second fundamental theorem of calculus by differentiating the result in part A. So you have something like this one. We want to integrate this, so it might be easier if we rewrite the square root of t as t to the 1/2. So we got integral t to the 1/2 dt, and then when we take the antiderivative, we're going to add 1 to the exponent and multiply by the reciprocal in the front. And we're evaluating from 4 to x. So our capital F of x equals 2/3 x to the 3/2 power minus 2/3 4 to the 3/2 power. And when you cube 4 and then take the square root, that's 8. Multiply by 2, divide by 3, you get 16/3. So now for part B, we're going to differentiate the result of part A. And this derivative is 0. Multiply 3/2 times 2/3, that's 1, and then this becomes x to the 1/2, so the derivative is x to the 1/2, or the square root of x. As you notice, it's the same thing as this, but with an x. Okay, so then we get to something a little more complicated. When you have a function here other than just x, something like square root of x, or really anything else other than just the one variable, we are going to follow the same pattern. We're going to take the antiderivative of the integral, which is sine of t, and we're going to plug in the square root of x and 0. So we got sine of the square root of x minus sine of 0. Since sine of 0 is 0, that just equals the sine of the square root of x. So again, the goal is to find f prime, capital F prime, and the derivative of sine of the square root of x is cosine squared of x, and then because of chain rule, we have to multiply by the derivative of the inside function. So the derivative of the square root of x is 1/2 square roots of x, and for if you're still doing the exponent, here's your original. We've got dy dx 1/2 x to the negative 1/2, which is 1/2 square root of 2. So in general, we can say that you're going to take whatever this function is and plug it into your variable t, but if it's a function and not just x, then you also have to remember to multiply by the derivative of whatever this function is. So, in general, for differentiating definite integrals, when the upper limit is a function, we are going to think of that function as u of x, and our f prime of x is going to equal f of this function, plug in this function for t, and then you have to multiply by the derivative of this function. Let's try this in another example. Okay. This one's fairly difficult. We currently cannot integrate this because if you tried to make this one plus t squared to the 1/2 power dt, we can't currently integrate that because that's got a complex function on the inside. We need something like chain rule, an anti-chain rule. So we're going to take that x squared and we're going to make that u, like we did in the general case before. We're going to write the variable limit as an integration of u equals x squared. So I've got f of u equals the integral from 5 to u of 1 plus t squared square root of that dt. And using the chain rule of derivatives, I'm going to take the derivative of x equal to f of u times u prime of x. F of u of x times u prime of x. So we've got this function, the square root, 1 plus u squared times the derivative of u, and so we already know that u is x squared. We know that the derivative of x squared is 2x, so finally we're going to get x squared for u and 2x for u prime and evaluate it out, and this is our f prime of x. Okay. We use this method pretty much to integrate without having to worry about like an anti-chain. Like this is the anti-chain rule. We have the square root. We plugged in our function in for t, so we had x squared squared, x to the 4th. And then the final step is multiplying by the derivative of whatever this function is, 2x. Our final example is a little bit more complicated because we have two functions as our limits of integration. Since we only know how to do it for one, what we're going to do is split up this integral so that we have only one variable on each integral. So I'm going to pick 0 as the place to split this up. So f of x equals the integral from x to 0 of sine of t squared dt, and then plus the integral from 0 to 2x of sine of t squared dt. We also need to have the function on the top, so I'm going to change the order of my limits of integration by making the first integral negative, which we can do with our properties. And now I'm going to take the derivative using the chain rule, anti-chain rule. So we've got negative and then sine of x squared, and then the derivative of x is 1, plus sine of 2x squared times the derivative of 2x, which is 2. So this equals sine of x squared plus 2 sine of 4x squared. And that's it. If you have any questions, feel free to see me in class, after school, during cab morning, or shoot me an email.